In this video, we're going to discuss the idea of inverse functions. Now, to kind of understand what's happening with inverse functions, let's start by looking at a simple algebra equation, but it might be one that maybe you're not comfortable solving using algebraic techniques. However, we should be able to look at this equation and figure out what the solution should be. So if I want to solve this, we're looking for a value that if I raise it to the third power, I get 8. Well, without doing any algebraic techniques, we should realize that if you take 2 and raise it to the third power, meaning 2 times 2 times 2, you get 8. So we know this should be the answer. All right, but what if we didn't intuitively know that? Well, then what I would need to do is find a way to undo this 3 in the exponent. Okay, now many of you may know this and many of you may not, but to undo the third power in the exponent, what you're going to do is you're going to take the cube root of that side, and of course, just like always, whatever you do to the left side, you've got to do to the right side. So this cube root will undo the cube, and what's left is just x. But on the other hand, the cube root of 8, just like a square root, asks us what number do I multiply by itself to make what's inside. A cube root says what number do I multiply by itself twice to make what's inside, and you'd multiply 2 by itself 2 times. So that would tell me that x should be 2. And so there's our solution. Now the concept that we use up here in this line is that we have the function, let's consider the function f of x equals x cubed. But then we also can consider the function, the cube root of x. Now the reason this whole algebraic process worked is because these two functions are inverses of one another. In other words, they can undo one another. So here, when we formally define what an inverse function is, we're essentially saying that if f, okay, if this function f, let me write it like this, if f, if f takes a and spits out b, all right, then my inverse function would be the one that does just the opposite, right? That basically undoes it. So the inverse, which we'll denote like this, f with a little -1 means f inverse, takes in b and spits out a. All right, and so notationally, we could see this down here. It says if f of a equals b, then f inverse of b is equal to a. Okay, so it's literally, just think of it like the undo button in a word processing document, right? It just takes you back to where you started. All right, so to kind of start to get a handle on this, let's take a look at this graph here. We've got 4 points here that are defined for the function f. So in part A here, it asks me to evaluate f inverse of -6. Okay, figure out what that is. Now, to just borrow the notation up here from the definition, since they're using f inverse of b equals a, let's go ahead and call this unknown a, okay, and try to find it. All right, so we're looking for the number that if you stuck -6 into the inverse function, that number would be output. But what this tells us is that if f inverse has an input of -6, then that means that -6 must be the output if you plug a into the original function, right? So all I'm doing is I'm taking this definition and I'm just writing out exactly what it means, but instead of b I have -6 in here, so that would mean -6 would have to be the output for the original. Okay, now I can figure that out because I go over to the graph here, and here's -6 on the y, so the output for the function f, and that's happening at x is equal to -3. So that means that a must in fact be -3. All right, so that's our answer for f inverse. We could do the same thing. F inverse of -4 equals what? Well, whatever it is, if I put it into f, it should spit out -4. So I go down to -4, and I can see that that happens at x equals -1. So that must mean this a is -1. All right, so then f inverse of 0 is equal to a. That must mean that if I put a as the input for f, it'll spit 0 out. So when we're at y equals 0, we can see that we're at an x value of 1. So a must equal 1. And then lastly here, we get the hang of this. F inverse of 1 is equal to a. So that means f of a equals 1. So when does that happen? Well, the y value is 1 on the original graph f when the x value is 5. Okay. And then the second thing they wanted us to do here is to graph the inverse function. Okay? So if I want to graph this, now that I have evaluated 4 different input values for the inverse and found the output value, that actually gives me 4 ordered pairs that I can graph. Okay, so when I'm graphing f inverse, I'm thinking of course, the number that's in here as the x and this as the y. Okay, so the first point that I could graph would be -6 in the x, -3 in the y, so that puts me right there. Then here I'd say -4 in the x, -1 in the y, so that puts me right there. Then I have 0 in the x, 1 in the y, that puts me right there. And 1 in the x and 5 in the y puts me right there. And I can go ahead and try to connect these up. Try to keep my line as straight as possible. Sorry, that's not the cleanest line there. Okay. Let me fix that middle one real quick because of the next observation I want to make. Okay, so there we go. So this is my inverse function. That essentially will undo the original function. All right, so on this next page, let me just go ahead and quickly reproduce the graph from the previous page. All right, so there's our inverse function. And I want to make a couple of observations about this. So first of all, I want us to understand that each of the points that are on this graph, so let's just pick them out real quick, -6, -3, -4, -1, 0, 1, and 1, 5. They have a very special relationship with these main points on the f of x graph. This point here is the point -3, -6. This point here is -1, -4. This point here is 1, 0. And this point here is 5, 1. So what you see is that if the point AB is on the graph of f, the point BA will be on the graph of F inverse. Okay, and that's always going to be the case. And that makes sense because basically what is happening is the inputs and outputs are switching for these. Furthermore, there's another little observation here. One thing that we can say is that these two functions are symmetric with each other about the line y equals x. Okay, let me grab another color right here. I don't know, maybe we'll use green. Okay, so here's the line y equals x. I'll kind of put that as a dashed line. Okay, so this green line y equals x, what we're saying is that these two graphs are symmetric about y equals x. And so another way of saying it is it's like F is looking at itself in the mirror if the mirror is the line y equals x. Okay, so that will always be the case for inverse functions, and that's a handy way to check to make sure that functions are in fact inverses of one another, is to make sure they are symmetric about y equals x. And the last thing I want to say is that because of this property where if AB is on the graph of f of x, then BA is on the graph of f inverse, another way of approaching that same idea is to say that their domains and range switch, because the x value is the domain and the y value is the range. Okay, so they literally we can say the domain of f is the range of f inverse, and the range of f is the domain of f inverse. And if you look at this example, the domain of f is what? -3 to 5, right? So this has a domain, in interval notation, -3 to 5. And it has a range, right, of y values of -6 to 1. But what you can see is that for the inverse graph in red, that is exactly its range, right? That's the set of y values that it goes over, and -6 to 1 is the set of x values that the inverse function goes over. All right, so lots of important observations here about inverse functions and specifically their graphs. All right, and one more property I want us to understand is the inverse function property. The inverse function property basically is just a reminder that f and f inverse undo each other. And so if you compose an inverse with its original function or a function with its inverse, then what you get is the thing you started with again. Okay, so you get x right back. And that's true as long as the x that we're talking about is actually in the domain of the inside function, and as long as, in this case, the x is in the domain of the inverse function. All right, so we will always have that property. So that's actually a way, this inverse function property is a way of checking to make sure that two functions are in fact inverses of one another. So in example 2, it asks us to convince ourselves that these functions are inverses of one another, both algebraically and graphically. All right, so algebraically, that just means that the inverse function property should hold. So all I'm going to do is I'm going to go ahead and do the composition of these functions. So first of all, let's do f of g of x. All right, so if I do f of g of x, that means I'm going to plug g of x in wherever I see an x in the original function here. All right, so that means g of x is 1 over x plus 1. Right, so I'm plugging the formula for g of x in for g of x here. But then 1 minus 1 is just 0, of course, so it's 1 divided by 1 over x. But we know that that just equals x. Okay, so when I compose them that way, I get x back just like the inverse function property says I should if they are truly inverses. If I go the other way, g of f of x, then I take g of x and instead of 1 over x plus 1, I say 1 over f of x plus 1. And f of x, of course, is 1 over x minus 1. But this, of course, is just x minus 1 because I'm going to, instead of divide by 1 over x minus 1, I multiply by its reciprocal, which would just give me x minus 1. And of course, I get x there as well. And you'll have to forgive me. Okay, so for example, right here, I'm kind of not really showing my detail work here. So what's going on, just to be clear, is I'm taking 1 divided by 1 over x, which is 1 times x over 1, which is just x. Okay, so that's how I'm getting that. And then I'm applying the same logic in this one. But they both equal x, just like the inverse function property says they should. So that allows me to be convinced that these functions are inverses of one another. Okay, so, and since it would work for any x, then I can feel free to say that, yes, these are true inverses. Okay, but what about graphically? What's that all about? Okay, so this is using our observation that these two functions should be symmetric with each other about the line y equals x. So f and g should be symmetric. This is our observation from earlier. About y equals x. Okay, so let's put those in a calculator. So first I'm going to go to my y equals menu. I'm going to say 1 divided by x minus 1. And then I'm also going to say 1 over x plus 1. All right. Okay, so I graphed both of those. Now, at first glance, things don't look so good. Okay, but the reason they don't look so good is, first of all, my window's all wrong, right? My y scale is much bigger than my x scale, so I obviously haven't changed this from a previous problem that I've done. So I'm going to go to start by going to zoom, and then go to standard, okay? And then that allows me to see things so that I have the same number of notches in the y and the same number of notches in the x. Okay. However, we still have a bit of a problem, because if I go ahead and put in a y equals x, and let me go ahead and do that. I'm going to go ahead and put in the graph y equals x. Right now, it kind of looks like maybe they're symmetric about y equals x, but at the same time, I'm not entirely sure. The reason that it doesn't look quite perfect is because on a graphing calculator screen, the y value notches are automatically closer together than the x value notches. And so to really get a much better view of this and really be convinced that these are symmetric about y equals x, what you can do is go to zoom, and you go to number 5, which is zoom square, and that squares things up, okay, so that the distance between the notches is the same. And when I look at it that way, it looks much better. It looks like literally this part of the red is looking at this part of the blue in the mirror, and same thing with this part of the red and this part of the blue. And so looking at that, I'm convinced that graphically I'm getting what I expect, right? That these are symmetric about y equals x. Okay, so let's look at example 3. Here's where we're going to actually take an equation and go ahead and find the inverse of that function. So here's our function, 7 minus 5x. Okay, so the steps to finding an inverse is to first rename the function y equals 7 minus 5x. Why is that? Well, because I don't want to haul around clunky notation like f of x when I'm trying to do algebra. So let's just give it f of x. It's the name that we're more used to, which is y. All right, number 2 then asks us to interchange x and y And the reason we're doing that is because we know that the domain of f and f inverse just swap with one another. So in other words, the x and y values swap with one another. So I'm going to start by writing it out like that. I'm going to, in place of y, I'll put an x. And in place of x, I'll put a y. Okay, because I know they're just swapping. And then lastly, what you have now is an equation where y is not by itself, but let's go ahead and get y by itself. So I'm going to subtract 7 from both sides here. X minus 7 is equal to negative 5y. And then I'll divide both sides by negative 5. So what I'll end up with is negative 1/5 x plus 7/5 is equal to y. And then what we realize is this y that we've solved for now really is f inverse, so now I go ahead and give it its proper name. F inverse of x is equal to negative 1/5 x plus 7/5. And that's our answer. So let's check our work from above. So we found that f inverse of x is equal to negative 1/5 x plus 7/5. All right, so let's check it with the inverse function property algebraically. So let's compose these two functions. So f of f inverse. And of course what we're looking for is that x pops out at the end. So f is 7 minus 5 times its input, but instead of x for the input, I'll put f inverse of x, which is 7 minus 5 times negative 1/5 x plus 7/5. But of course, as I distribute my negative 5 through to both of these terms, in that first term I get positive 1x, negative 5 times negative 1/5. And then in this term I get minus 7, which of course simplifies down to just x. And similarly, if I compose them the other way, f inverse tells me to take negative 1/5 times my input, but my input is f of x, and then add 7/5. But then f of x is 7 minus 5x. So when I distribute negative 1/5 through, we get negative 7/5 plus x plus 7/5, and so once again x is all that survives there. So we're getting what we expect, right? When you apply a function and then you undo it, you should get your input back again. And then we'll also check it graphically. So let's go ahead and graph this. And so I've typed in 7 minus 5x for y1. I've typed in negative 1/5 x plus 7/5 for y2, and then I've plotted y equals x. And then remember, the trick is it's always best to look at a squared up version of your axes. So first, if I just do zoom standard first, if I go 6, you can kind of believe maybe that those are symmetric about y equals x, but it's not. It's because of there's so much more space in the x notches. You're not necessarily convinced of that. So we go to zoom square, which is number 5, and then that's going to look a whole lot better.